Welcome back, everybody. Today, we are going to continue with our discussion of least squares. So just to remind everybody of the setting, we start by being given training data. So in particular, we have features xi, and we think about each of these as being a vector of real numbers with p different elements. And we have labels yi, and so in a classification setting, this might be plus or minus ones, or we might represent the labels with zeros and ones, or in a regression setting, they just might be real numbers that we're trying to predict. And so now our goal is, this is the training samples are for I equals 1 to n. So we've got a total of n different training samples. Now our goal is to predict a new label y for a new feature x. And the way we are going to do it is using a linear model. So specifically, our prediction is going to have the form W transpose X, where we take the inner product, or in other words, we are going to have the sum from J equals 1 to P of weight J times this vector X's jth element. And so if we were, for instance, looking at what prediction we would be making on our ith training sample, then we'd be taking the inner product of W, our weight vector, with Xi, and we'd be multiplying in the sum by the Xij's. And so our hope is to find a weight vector, W, so that this weighted sum is close to the training label Y that we have. So we're going to use our training samples to find a good weight vector. So we said before that we can write this a little bit more simply using matrix vector notation. So we could have a label vector, Y, which just has labels Y1 through Yn in it. And we could also have a feature matrix X, where the first row is the first feature vector transpose, the second row is the second feature vector transpose, all the way down to the nth row, which is the nth feature vector transpose. And so altogether, this is a matrix with n rows and p columns. And so our linear model can now be written like this. We want our weight vector W so that this label vector Y is close to this feature matrix X times our weight vector W. So what we looked at last time was least squares, where what we wanted to do was to find the W that would minimize the sum of all the squared differences between the training labels and the predicted labels. So we tried to minimize Y minus XW, and we wrote this as this 2 norm, or equivalently the 2 norm squared. So we wanted to minimize this, and what we derived was a least squares weight vector that had the form X transpose X inverse X transpose Y. But we were left hanging a little bit because a core question that we had not addressed is, when does this matrix X transpose X have an inverse? When can we even compute this least squares expression? and what ensures that it's nice and well defined. And what we claim is that this exists, this inverse exists when X has P linearly independent columns. So what we're going to do to start off today is to talk about this notion of linear independence, what it means mathematically, look at a few examples, and connect it to the notion of computing this inverse and seeing why that's important for us to have a good least square solution. On an intuitive level, remember that these different columns of X, these P different columns of X, correspond to different features. So let's think about this running example we've been talking about, where we've got measurements of people's facial features, and we want to predict whether their photograph represents smiling or not. Let's say that one measurement corresponds to left eye corner to left mouth corner distance, and another feature corresponds to right eye corner to right mouth corner distance. If all n of the people whose photos we have are just perfectly symmetric people, then those distances would be equal, and those features would be indistinguishable from one another. And so this would be an example of a case where we have two features that are not linearly independent of one another. Because those features are indistinguishable from one another, we cannot compute this simple least squares formula, and we have to turn to more sophisticated methods that we'll talk about later in this course. But first, let's focus on this notion of linear independence and when we can compute this matrix inverse. So we say that a set of P vectors, V1 through Vp, all of which are in Rn, is linearly independent if and only if we can write a weighted sum of these vectors. And the only way that that weighted sum can equal 0 is if all the weights are 0. Okay, so a little bit more specifically, if I were to write a sum from j equals 1 to p of aj times vj, then if this is equal to 0, then that implies that all of the aj's are also equal to 0. And similarly, if all the aj's are equal to 0, then the weighted sum is equal to 0. Okay, so then these vectors are linearly independent. And another way of thinking about this is that there's no way I can write any of the vj's as a weighted sum of the other remaining vj's. And so let's look at an example that I want to make sure is crystal clear. And in this case, we are going to have n being equal to 3. So we're going to have each of these vectors have 3 different entries. And p is equal to 4. So each one of them is going to have 4 different, I got that wrong. Each one is going to have n entries, and I'm going to have 4 different vectors. think I wrote it wrong, right, and said it wrong. So my V1 is going to be 1, 0, 0. V2 is going to be 0, 1, 1. V3 is going to be 0, 1, 0. And V4 is going to be 1, 0, 1. So now the question is, are these vectors linearly independent or not? And so if we were to look at A1 V1 plus A2 V2 plus A3 V3 plus A4 V4, and just write that out, in this case it's a nice simple expression. So in the top we would have A1 plus plus A4. The second entry would be A2 plus A3. The third entry would be A2 plus A4. Let's make sure I got that right. And so what happens here is that it's possible to find combinations of the A1, 2, 3, and 4 so that each one of these entries is equal to 0 without the A's all being equal to 0. Right? So in other words, I can write one of these V's and it's a weighted sum of the other V's. So just to be explicit about it, if we had A1 was equal to negative A4, which is equal to A2, which is negative A3, then this weighted sum that I have written on the board would be equal to 0. Okay, alternatively, we can do this explicitly, writing one vector as a weighted sum of the others. And in fact, in this case, V4 is equal to V1 plus V2 minus V3. And so from this, we can conclude that these vectors are linearly dependent. They are not linearly independent. And in general, a key point is that if you have linear independence, it implies that P is going to be less than or equal to n. And if you have P greater than n, like we do in this example, then it implies that your vectors are going to be linearly dependent. So when we're working with machine learning, like the classification problem that we started off with, or the regression problem that we started off with, we typically like to work in the regime where the number of features, P, is smaller than the number of samples, n. This is the case in least squares. When people talk about over-parameterized machine learning, they might be working in the regime where P is greater than n, and where the least squares techniques that we're talking about today will not necessarily work, or not. You can't just use the formula that I wrote on the board, and you have to start looking at other methods. But in the context of least squares, as we're learning it here, we need to have the number of features be less than or equal to the number of training samples available. Another important concept that we touched on earlier is that of matrix rank. And the rank of a matrix is simply equal to the number of linearly independent columns. And that is equal to the number of linearly independent rows of X. They're the same thing. Now, this notion of matrix rank is something that's going to show up throughout this course, and we're going to see it from multiple different perspectives. We're going to see different ways of thinking about the matrix rank. But for now, we can think about it simply as this number of linear independent columns or rows. Yes?
For p less than or equal to n case, I feel like you can also construct like a matrix where it's still linearly dependent.
Right, so these arrows are not going both ways. So I'm saying if it's already linearly independent, then p must be less than or equal to n. But you can certainly, this is a great point, you could certainly construct a matrix where p is less than n, but you do not have linear independence, right? But I'm just saying, if you know it's linearly independent, then you must have p less than or equal to n. Fantastic point. Are there any other questions? Yes?
So for linear independence, why can't we predict it's p smaller or equal to it instead of p equal to it? Because for this case, the maximum rank should be p, and for n, there is definitely going to be some like linear independence if n is larger than p, right?
Okay, so I think your question was, why does linear independence not require that p is equal to n? But certainly in one of the examples that we've covered in the past, you can have p less than n and have linear independence. So let's just do a very quick one. So here's an example where n is equal to, what was it? N is equal to 3 and p is equal to 2. And so my first vector is going to be the same as my first vector in our previous example, 1, 0, 0. And my second vector is going to be 0, 1, 1. So these two vectors are linearly independent. I cannot write one as a weighted sum of the other.
But its rows are linearly.
Okay, we don't really talk about the linear independence of rows in a vector. So we're really just talking about linear independence of a set of vectors here. So we're talking about whether the set V1 and V2 are linearly independent or not.
We focus on the columns.
In the context of least squares, we said that we can use this formula when the p columns of x are linearly independent. Yeah. Okay. And so from here, we have that, the following. So I'm going to just make a claim, and we're going to, there's a little bit more detail in the printed lecture notes online, and we're going to flesh it out a little bit more later today. But specifically, if the p columns of our feature matrix X are linearly independent, then, first of all, if we were to compute X transpose X, and this is called a gram matrix, it also has p linearly independent columns. And so another way of thinking about this is X transpose X is a matrix that has p rows and p columns. And since it has p linearly independent columns, the rank of this matrix is p. Rank of X transpose X is equal to p. And these two things, the fact that this matrix has rank p and is p by p, tells us that X transpose X is invertible. And so we were a little bit rushed when we tried to cover this before. And so let's go through it now. Matrix inverse. The inverse of a square matrix A, which we write as A to the power -1, is the matrix A that satisfies that if I were to take A inverse and multiply it by A, or if I were to take A and multiply it by A inverse, either way, I'm going to get an identity matrix. And just as a reminder, an identity matrix is a matrix where I've got all ones along the diagonal and every other entry in the matrix is 0. And so just as a little aside, right, if I told you about, 10 inverse, then this is just equal to 1 over 10. And so if I think about my matrix A as being a 1-by-1 matrix with value 10, then A times A inverse would simply be equal to 1. So it's conceptually related to this notion of inverse that you have encountered before. And so my claim over here is that now if our matrix X of features has P linearly independent columns, then the Gram matrix X transpose X is invertible. And then we can use this formula that we have on the top that the camera is not capturing. There we go. That we have on the top in order to compute a least squares solution. Yes?
The term Gram matrix, is that just...
Yes. So we can derive using the fact that just the form of the Gram matrix and the fact that the P columns of X are linearly independent, we can derive that X transpose X also has P linearly independent columns. And that's written out in some detail in the online notes. Yeah, I'm just not going to cover it in class today. Okay, great. And so then going back to least squares, here we go. The final thing that I wanted to mention is just going back to this geometric perspective that we drew out last time. And so if you recall, we had the span of the columns of X, and we were writing these different vectors in it. So we had here, this was the span of the columns of X, or the range of X. And so here was our origin, and here we had the first column, and here we had the second column. And then we had our label vector y, and we said that the vector in this span that was as close as possible to y, that minimized the distance, and we called this vector r, so that minimized that r, we called this y hat. And so this y hat is now corresponding to our x w hat. So this is the formula that we derived, where w hat is equal to x transpose x inverse x transpose y, gives us the set of weights, so that when we compute y hat equals x w hat, that y hat is the vector in this span of the columns of X that's as close as possible to our label vector Y. And if we were to expand this out, so I've got X, and then I put in, my W hat, so now I've got X transpose X inverse, X transpose Y. What I'm doing here is I'm taking my label vector, and I'm multiplying it by this big matrix here that's composed of all the features that I've collected in my training set. And this matrix also has a special name. This is called a projection matrix. And our geometric picture of least squares gives us a sense of y, because it's sort of like we are projecting y onto the span of all of the columns of X. So the projection operation is finding this closest vector. another way of maybe thinking about it is imagine that, the span of the vectors is just like the blackboard, and I've got some vector y whose point is out here, and I shine a projector on it and I see where that point lands, then that's going to tell me what y hat is. So I am just projecting my original vector y onto the span of the columns of x. Any questions about this? Okay, so we derived all of this from this geometric perspective. And it allowed us to get introduced to a lot of core concepts like span, linear independence, and rank, and inversion of matrices. But now what we're going to do is we are going to derive this same expression for least squares from an optimization perspective. And this is, you're going to think, well, why? We already know what the formula is. But this is going to allow us to learn a little bit about optimization that's going to be extremely useful later on when we get to problems where there isn't a simple formula that can describe the optimal value and where we have to compute it numerically using optimization tools. So we're going to be thinking about this same problem now from a new perspective in order to acquire some new skills that'll be super valuable downstream. Yes? Okay, I don't know if I completely heard you correctly, but I think what you said was in this expression that we have over here, we are taking this vector y and multiplying it by a collection of matrices. And you asked, how do we know when this product is going to also be a vector? Is that right?
Yes.
Okay. So there were some kind of diagrams I tried to draw in the notes and on the board. I always think about it myself just in terms of dimensions. So y I think of as being an n by 1 vector, n rows, 1 column. So x, remember, is n by p, and that means that x transpose is going to be P by N. So here I've got a P by N matrix. And then X transpose X, so I'm just going to do this one off to the side. X transpose X is going to be P by N times N by P. And so when I'm multiplying two matrices together like this, I think of these inner dimensions as canceling out because this is where I'm taking my inner products. And so the result is going to be a P by P matrix. So down here I've got something that's P by P. And then finally I've got N by P. And so again, whenever I'm doing these multiplications, I think of the inner dimensions as canceling out because each inner dimension is like rows and vectors that I'm taking inner products of. And so those cancel out, and those cancel out, and those cancel out. And this tells me that this entire product now is going to be n by 1, or a vector with n entries. Yeah. I don't know if that's the level of intuition you were hoping for, but yeah. I guess the other thing I would mention is we said that this matrix right here is a projection matrix. And so for projection matrices in general, they are going to be square. In this case, it's n by n. Because we're taking a vector in dimensions, and we're projecting it onto this span, but it's still in an n-dimensional space. So the kind of vector we're multiplying by and the output that we're getting back are both the same length vector, which is what we would hope for. Yeah. Any other questions? Okay. All right, so if we recall the way we set this up, we said that W hat was going to be the argument W that minimizes the sum over all of our training samples of the residual Ri squared associated with W. And just expanding that a little bit, this is the sum from I equals 1 to n, and then the residual is just the difference between our training label yi and what we're going to get out of this least squares predictor, which is the inner product of xi and w, and then square that. So our w hat is going to make this sum of squared errors as small as possible. Now we can write this same thing with our vector notation. So this is the arg min over w of, if I form my residual vector, I'm just taking the norm of that vector squared. And for my expansion here, it's the argument w that minimizes y minus xw squared. So again, this comports exactly with our geometric picture. We're just trying to make the length of this residual vector r as small as possible. And then we are writing that residual vector explicitly in terms of our matrices and vectors. Now we're just going to expand this a little bit. So in particular, when we take the norm of a vector, remember that's just that vector inner product with itself. And so what we have here is y minus xw transpose times y minus xw. And this is just using this notion of the Euclidean norm. And now what I'm going to do is I'm going to expand this even further using the same kind of FOIL trick that you guys learned in algebra, but now applied to vectors and matrices. So we've got the argument w that minimizes. And so first I'm going to multiply the two first terms here, y and y. And so I'm going to have y transpose y. Then I'm going to do the outer terms. So I'm going to multiply y transpose times xw times negative xw. And then I'm going to have the inner terms, so xw transpose and y. So I've got xw transpose times y. And then finally the last terms, so plus xw transpose xw. Any questions about this so far? Okay. And so now we've got y transpose y, and we've got y transpose xw. And then we have here a transpose of this product of x and w. So when we're doing the transpose of a product, what we do is we take the transpose of each factor in the product and we reverse the order. So this is going to be minus w transpose x transpose y. And similarly for this last term, we're going to have plus w transpose x transpose x w. And the final thing that I'm going to do is I'm going to use the fact that y transpose xw and w transpose x transpose y, those are the same thing, right? They're both scalar values. One, I've written one as the transpose of the other, but since they're scalars, transposes don't matter. So they're exactly the same thing. So I'm going to combine my terms. So I'm going to have the arg min over w of y transpose y minus 2 w transpose x transpose y plus w transpose x transpose w. Okay. So now we have an expression here in terms of our matrices and vectors. And we want, what this is saying is we want to search over all possible W's and find the W that's going to make this expression as small as possible. And this is very related to things that you have already encountered in calculus. And so we're going to start off with a simple scalar example and then build from there. But already you can see hints that we are going to be headed towards something that is, as we would hope, exactly what we derived from the geometric perspective, right? We're already seeing here this X transpose XW and this X transpose Y, which showed up in our system of equations that we were solving last time from the geometric perspective. Okay, yes?
Can you explain the ending of that second line again, where we have y minus xw, how these two things are equal to each other?
So how these two are the same?
Yes.
So just in general, if I were to have the Euclidean norm of a vector squared, just what this notation means, I'm not really like doing anything fancy. This just means R transpose R. That's all. And so now I'm just doing the same thing with y minus xw. I'm just replacing R with y minus xw and putting it in parentheses.
It's like the property of the squaring the norm.
That's right. I wouldn't even call it a property, more like the definition. So it's not like I've done something advanced here. I've just like plugged in the definition. Yeah. Yes?
So when we're, because this is the minimization problem, and y transpose y is going to be the same for any value of any set of weights we choose, can we remove it from the equation?
Absolutely right. That's a super insight. I was going to get to that very quickly for the video. The question was, well, y transpose y is going to have exactly the same value no matter what we choose for w. So why are we even bothering writing it down? Is this necessary or can we get rid of it? And yes, we can absolutely get rid of it. It won't matter in the least. Excellent insight. Okay, so yes, let's do a little warm up here. Oops. And just think about finding the minimum of a function in the scalar world that we all are familiar with. Is the red easy to read? Yeah, okay. So imagine that we have a loss function, L, that depends on a variable W. And just to be clear, over here, this thing that we're minimizing, this is our loss function. This is our loss associated with W, where the loss corresponds to the sum of squared errors. So now we're going to imagine a simpler loss function, which is simply 1/2 W squared minus W minus 1/2. And we can make a plot of this function. So on this axis, we've got W, and on this axis, we've got our loss associated with W. And it looks something like this. And we want to find the value of W for which this is as small as possible. So here's the minimum, and this is the W hat here that we are going after, the minimizing value of W. Okay, so the way that we learned to approach this in calculus would be to compute the derivative and set it equal to 0. So the derivative of L with respect to W. So take the derivative here. So we've got 2 times 1/2 is 1. So we would have W. And then we would take the derivative of the linear term and we would just have minus 1. And then we take the derivative of our constant. It's 0. And so our derivative is simply W minus 1. We set that equal to 0, and that tells us that our W hat is equal to 1. So right here, this is equal to 1. Okay, simple concept. In order for this to work, of course, this function has to be convex, or in this context, bowl-shaped, as opposed to a hump. Otherwise, we'd be finding a maximum instead of a minimum. So all of these concepts are going to now show up as we think about least squares from an optimization perspective. It's just now we're going to be working with matrices and vectors instead of scalars. But we're still going to be doing things like, or analogous to, taking derivatives and setting them equal to 0, and making sure that the function we're minimizing is nicely bowl-shaped, so we're finding minimizers as opposed to maximizers or something else. Okay. So the first notion that we need to introduce here is a gradient. And this is just analogous to a vector. I'm sorry, analogous to a derivative, but for vectors. Okay, so in particular, I'm sorry, I keep putting this on just do not disturb, and I keep getting messages. Okay, so gradient. So we have a loss, L, that is going to take in a vector, W, and output a scalar, say the sum of squared errors. And so now the gradient of L with respect to W is the following. I'm going to write this as the gradient of L, and then I'm going to put a little W down there in order to indicate that I'm taking derivatives basically with respect to W. And all I'm going to do is just compute a whole bunch of derivatives with respect to the different elements of W. So first I'm going to have the derivative of my loss with respect to the first weight. And then I'll have the derivative of the loss with respect to the second weight, all the way down to the derivative of the loss with respect to my final pth weight. So the gradient is simply this vector of derivatives where I've got one derivative for each one of the different weights that I'm trying to learn. Okay, so we're going to now work through 4 critical examples of gradients that are going to be very essential to our notion of least squares and to give us some core concepts. And so the first one is where my loss is equal to W transpose C, where C is just a vector of constants. So C1 all the way to CP. So I want to know what is the derivative of this. So recall this notion of inner product tells us that this is just W1C1 plus W2C2 all the way to WPCP. So now if I want to compute the gradient of my loss with respect to W, then I'm computing first the derivative of this loss with respect to the first weight. And what is that? C1. And with respect to the second weight? C2. Excellent. And so forth all the way to CP, which is exactly this. So in this example, the gradient of this loss, which is just the inner product of a weight vector and a constant vector, is simply that constant vector. Make sense? Okay, let's work through a few other examples. So here, my loss is going to be the 2 norm of W squared, or W transpose W. And if we were to write this out the long way, we would have W1 squared plus W2 squared all the way to WP squared. And so now if I wanted to compute the gradient of this loss with respect to W, first I compute the derivative with respect to W1, and what do I get? 2W1, and then 2W2, all the way to 2WP. And so this is simply 2 times my original weight vector, which hopefully these should feel comforting, right? Like if we simply had in our first example, if these were scalars, right? And I had a function that was a constant times my variable and I take the derivative, I would just get the constant back, right? That's what I would hope. Similarly, if in example 2, we had a quadratic expression or a quadratic function and we took the derivative, we'd expect 2 times our variable to pop up, right? Like if we had f of, anyway, sorry. So this is consistent, if p was equal to 1 and everything were in the scalar case, it's consistent with everything we're experienced with derivatives. Okay, now the third example is super important. We're going to use this a lot, but the derivation is a little tedious and we're not going to go through it all here in class. But the example is where the loss with respect, or the loss of W is equal to W transpose times some matrix, square matrix, Q times W. So in this case, it's a little bit like example 2, only we've got this Q matrix popping up. And so writing out the expression for the loss in longhand is, like I said, more tedious. But in this case, it is possible, if tedious to work out, the gradient of L with respect to W is equal to Q times W plus Q transpose times W. And if Q is symmetric, which means that Q and Q transpose are the same matrix, then the gradient of this loss with respect to W is 2Q times W. Okay. So our final example my loss as a function of W is equal to Y transpose Y minus 2W transpose X transpose Y plus W transpose X transpose X transpose W. Okay, so we want to compute the gradient of this function, which, if you recall, is our least squares loss function, right? And now we can put all the pieces that we have together. So the gradient of our loss with respect to W, as we pointed out before, this is a constant, doesn't depend on W at all, so that gradient is just going to be equal to 0. Now if we look at this term here, what example have we already seen that can help us here? Right, this is just like example 1. We have got W transpose times a vector that doesn't depend on W, so it's a constant relative to W. And so we are going to be left with that constant vector, which in this case is 2x transpose y. And for this expression, what can we use in order to compute this gradient? Yes?
We need example 2, so that would be
Okay, this is my fault for not labeling it because I think you're thinking exactly along the right lines. So in this case, we do have this matrix X, transpose X, showing up in here. And so this is the form of the previously unlabeled example 3. And so, just like you were saying, we now have 2 times X transpose X W showing up. Make sense? Yes.
Sorry, this is
So the loss function it's a function. So it's like a mapping. So it's taking a vector in and outputting a scalar, which I think is what you were saying. And then you're saying, well, why is the gradient then not a scalar and instead a vector? So that's an excellent question. It's a little bit hard to draw, but I'm going to give it a shot here. So let's imagine that our loss function is sort of like this bowl-shaped thing. So here I've got weight 1, and this direction is my weight 2, and this direction is my loss with respect to my weight vector. So if I were to, sorry, I'm just not great at drawing this, but imagine that I'm at a point here, and I want to compute the gradient. The gradient is telling me, how is this loss changing in the W1 direction? And then separately, how is it changing in the W2 direction? So even though the loss only has a scalar value, the gradient is telling me how much it's changing or how quickly it's changing in each of the different directions that the function depends on. Yeah, great question. Any other questions? Yeah. Yes.
Here, Q is a square matrix.
Yes, that's right. And Q would have to be square in order for our dimensions to work out. So here, W is a P by 1 vector. So W transpose is 1 by P. And so in order for this multiplication to even be possible, Q would have to be P by P. And of course, by the same dimensions canceling out argument that we had earlier, this product is going to be just a scalar or a 1 by 1. Great. Any other questions? All right, so now that we have this expression for the gradient of our loss, remember that we wanted to compute the argmin with respect to W of this particular loss of Y transpose Y minus 2 W transpose X transpose Y plus W transpose X transpose XW. And so our inclination would be to take the gradient and set it equal to 0. So let's just see what happens if we do that. So set gradient to 0. So we would get here negative 2 X transpose Y plus 2 X transpose XW is equal to 0. Now I'm going to divide both sides of my equation by 2. Simplifies things right off the bat. Now I'm going to move my negative X transpose Y to the other side so that I have X transpose XW is equal to X transpose Y. We derived exactly this equation when we were looking at things from the geometric perspective. And if X transpose X is invertible, then this tells us that the solution to this optimization problem will look like X transpose X inverse X transpose Y. So from this optimization perspective, we have derived exactly the same formula for the least squares solution. But again, this hinges on X transpose X having an inverse. So we talked about that a little bit from this notion of linear independence and matrix rank. But I want to talk about it more now from this perspective of optimization and when we can expect our optimum to correspond to this formula. Are there any questions so far? Okay. So recall that when we were talking about finding the minimum of a function back in calculus, we would take the derivative and set it equal to 0, but that depended on the function being convex or kind of bowl-shaped. Otherwise, we would risk finding, say, a maximum or some other point that is not the minimum we seek. And so now what we want to do is to think about what's the analog of that concept in this vector setting that we are in now. Okay, so in particular, we're going to talk about positive definite matrices. And this is important because if we have a matrix X that is n by p, where n is greater than or equal to p, and the rank of X is equal to p. So X has got p linearly independent columns. Then we know that X is invertible, or X transpose X is invertible. And we also know that X transpose X is positive definite. Okay, so this is not a definition. I'm going to define it in just a second. But the claim here is that this notion of invertibility, which is shown up a couple of different times now, is intimately connected to this notion of positive definiteness. So when we think about positive definite matrices, one of the reasons that we care about this is it is telling us when we can perform this matrix inverse that's essential to this machine learning procedure that we've derived. So a matrix Q is positive definite. And we write this sometimes as PD, or we might say that this matrix Q, we write it as sort of this curly greater than sign and then a 0. So both of those things correspond to positive definite, PD or Q curly greater than 0. If, whenever we take a vector W and compute W transpose QW, that this is greater than 0 for any vector W that is not equal to 0. Okay, so clearly if W is equal to 0, then this product is 0. But aside from that, for any other weight vector, if we were to compute W transpose QW, that has to be 0 in order for the matrix Q to be positive definite. We can also say a matrix Q is positive semi-definite. And I really think mathematicians come up with funny names for things sometimes. But PSD, or we write Q and we have got this curly now greater than or equal to sign 0. If W transpose QW is greater than or equal to 0, well, for all W. Okay, so this, I think, right now feels very abstract. And so what I want to do is to now connect these definitions to the optimization framework that we've been working in today. And think about the geometry of the optimization problem and how it relates to positive definite matrices. Okay, so let's start where W is, I guess I won't even write the underline, just a scalar, and so is Q, right? So we're going to work with a very simple scalar setting first. And so then this notion of W transpose QW, when everything's a scalar, is just Q times W squared. And so the question is, when would QW squared be equal to 0? Well, this is always greater than 0 if W is not equal to 0. We want to know if Q is positive definite or not in this scalar toy setting. So we want to know when QW squared is greater than 0, assuming that W is not equal to 0. And so when will that happen? For what values of Q? Any thoughts? When, I think I heard this murmuring, whenever Q is positive, right? So if W is non-zero, positive or negative, and I square it, I'm going to get a positive number. So as long as Q is positive, the product's going to be positive, right? So in this case, a positive definite scalar Q is just a positive number Q. But now we can see why this is relevant, because we can say, imagine trying to minimize a loss L of W equaling QW squared. And so we can consider the case where Q is a positive number. And again, we're going to plot W versus our loss, L of W here. And when Q is a positive number, then this loss function is going to look like a simple quadratic, like that. And so this is a setting where we can take this, compute its derivative, set it equal to 0, and find a minimizer. But in contrast, if Q was less than 0, then we are no longer in this positive definite setting. And now if I make a plot, again, W and L of W, then all of a sudden this loss function, it looks like a quadratic, but it is flipped the other way. So now in this setting, if I were to take the derivative and set it equal to 0, I would find a maximizer, not a minimizer. Yes? So in this example, I am just to kind of illustrate the concepts, right? I'm thinking about P is equal to 1. So I'm still thinking about Q as being a P by P matrix. Nobody really worries about positive definite scalars. I'm just trying to connect this notion of positive definiteness to things that you're already familiar with in calculus, where you're trying to find extreme values of functions in one dimension, because hopefully they'll make the concepts in higher dimensions a little bit more accessible. So I'm just trying to say, well, what this notion of positive definiteness, what that special case looks like when P is equal to 1, and what effect that has on the loss function we're trying to minimize in this special toy setting. Yes?
Are we allowed to say W transform QW equals QW squared? Because I thought
In general, you cannot. In general, this would not be true. But when we're in P equals 1, when everything is a scalar, then these two things are equivalent, and only then. Otherwise, we can't do it. Right. Any other questions? Okay. So another way of saying this is that, and this is going to generally be true, when Q is positive definite, then things are easy to minimize for this loss function. And over here, when Q is not positive definite, then things are hard to minimize. Okay, so this notion of positive definiteness is related to our ability to minimize different functions, at least using the different techniques that we've been describing so far. All right, so now let's move to higher dimensions and see how these ideas manifest there. Okay. So now we're going to have P is equal to 2. So our weight vectors have 2 dimensions. And so W is in R2 and Q is in R2 by 2. It's a 2 by 2 matrix. And now we could imagine trying to minimize L of W is equal to W transpose QW. So, for instance, we could have Q being equal to 1, 0, 0, 1, just an identity matrix. And so, for this case, W transpose QW is simply going to be W transpose W, or W1 squared plus W2 squared. So remember our definition of positive definiteness said that this matrix Q is positive definite whenever this product, W transpose QW, is positive for any W that's non-zero. So in this case, in our example here, for this particular Q, W transpose QW has this form here. When is this positive? Yeah, for any W not equal to 0, this is going to be positive. And so, as a result, we can infer that this Q is positive definite. And like we were doing in the 1D case, we can try to make a plot. So this axis is my W1 axis. Vertical is L of W. And then I've got my W2 axis here. And in this case, the function that we are trying to minimize is going to look like a bowl. And I don't know, imagine that there's some contour lines here. So we've got a nice sort of bowl-shaped function here. And so you can imagine then, if we were to take a function like this and compute its gradient and set its gradient equal to 0. What does that mean? It means finding a point where I look and see how much the function is changing in the W1 and W2 directions and figuring out where there's no change, where the function is not, where the derivative is 0 in all directions, which is right here at the bottom of the bowl. So the fact that Q here is positive definite is correlating with a loss function that is nice and convex or bowl-shaped and easy for us to minimize using this technique of taking the gradient and setting it equal to 0. Now in contrast, we could consider a different Q matrix, which was, here we go, -1, 0, 0, -1. So in this case, if we were to look at W transpose QW and try to write out in long form what we get, this is going to equal negative W1 squared minus W2 squared. Is this always positive? No, right? If I were to take some W not equal to 0, I square the two values, I get two positive numbers, but I multiply them by -1, I'm going to get something negative. This is less than 0 for W not equal to 0. If I were to try to make a plot of a loss function of this form, W transpose QW, then what I'm going to see is something that looks like an upside down bowl. So similar to the other one, but now just upside down. And so here, the fact that Q is not positive definite. So here Q is not positive definite, is corresponding to a loss function where if we were to take the gradient and set it equal to 0, we're going to find a maximizer instead of a minimizer. Yes?
It seems that on some dimension could be counted. Like if, for example, if Q is 1 this one, in that case, is it as
This is a great question. In fact, that corresponds exactly to my next example. It's almost as if all the lecture notes are online. I'm just teasing. It's fine. This is a great question. Okay, so my next example is where we've got the same two-dimensional setting, but Q is equal to 1, 0, 0, -1, right? And so now if we were to look at what does W transpose QW look like and spell it all out, we get W1 squared minus W2 squared. And so for some W vectors, this will be positive, and for some W vectors, this will be negative. But in order for Q to be positive definite, it always has to be positive. And so in this case, Q is not positive definite. And if we were to plot this function, or the loss associated with this Q, then we get something that in the W1 direction looks bowl-shaped, but in the W2 direction looks upside down bowl-shaped. And so I'm getting these contours where if I were to hold W1 fixed and try to vary, if I were to hold W2 fixed and try to vary, let me get this right. If I hold one fixed and keep and vary the other, then I get a nice convex function where the minimum corresponds to where the derivative is 0. But if I were to look at a different direction, I get this upside down bowl shape. And so the place where the derivative is equal to 0 might be a maximum. And so if I look at a place where the derivative with respect to both W1 and W2 is equal to 0, where the gradient is equal to 0, then I guess in this example, it's right here at the origin. It's called a saddle point. So it's a minimizer in one direction, but a maximizer in another direction. So if you think about the literal shape of a saddle when someone's riding horseback, it's corresponding to this point where you have like the minimum with respect to one direction and maximum with respect to another direction. Okay, so this is another setting where if we just look for the place where the gradient is equal to 0, we will not have a minimizer of our loss function. Fantastic question. And we can do more complicated Q matrices that are that also connect to these concepts. Okay, so within the notes, there's a number of different properties of semi-definite matrices, and we're not going to go through all of them here in the lecture. But there's one that I really want to emphasize because it's super important for this class, which is for any matrix X. If we were to compute Q is X transpose X, so now Q is a square matrix, then that matrix is positive semi-definite. And similarly, I don't know, Q tilde, some other Q that's equal to X transpose, that's also positive semi-definite. And so now the real question is, and I derived this in the notes, but we aren't going to have time to do it today. If the columns of X are linearly independent, then if we were to compute Q as being X transpose X, then it is positive definite. And as we said before, this implies that it is invertible. And so, when the columns of our matrix of features X are linearly independent, then this gamma matrix that shows up in our optimization formulation and in the set of equations that we derived from the geometric perspective, in that setting, that matrix is positive definite and it is invertible, so we can use the formula for least squares that we've been using. And in this setting, this notion of positive definiteness is telling us when the function that we are trying to minimize, when this loss function is convex, where we don't have to worry about it finding a maximizer or a saddle point, but rather the place where the gradient is equal to 0 is in fact a minimizer of our loss function. Any last questions? Yes?
So when it says for any X in that right side, are all these conditions to that last line that you're saying? Like, are those first two lines conditions to if the columns of X are linearly independent then?
I was just trying to make two separate statements here. But here I think, yeah, for any X of real numbers where you've got linearly independent columns and the number of rows is bigger than or equal to the number of columns, then we would have this property, and we can use all of the least squares formulas we derived. Great. Thank you very much, and I'll see you next week.